What we're going to do today in this video is look at the definition of an empirical and a molecular formula, and then I'm going to show you how to basically use the percent composition that we calculated in the last video to actually figure out the empirical and molecular formulas of different compounds. So let's get started. First off, your definition, you need to know what these are in order to know how to calculate them. So first off, a molecular formula, it indicates the actual number of atoms in each element that makes up a molecule, whereas an empirical formula gives the simplest ratio between the atoms of the elements present in a compound. So in other words, this one is your reduced version, and this one here is not reduced. So let's go through some examples so that you see what I mean. Oh, of course. So note, number one, the formulas for ionic compounds are always empirical formulas, again, because you reduce them. And a molecular formula is usually a whole number multiple of an empirical formula. So let's just check this out, for example. Here are three empirical formulas and molecular formulas or chemical formulas. So you can see right here, I've got welding gas, okay? So the empirical formula for welding gas is CH, okay? And the empirical formula for glucose is CH2O. And then the empirical formula for benzene, which is a solvent, is CH. So you notice that the empirical formula for both acetylene gas and benzene, which is a solvent, is actually the same. Here's where it kind of gets a little bit interesting, is that we can have different whole number multiples to make your chemical formula. So your acetylene gas in molecular formula, so this is the actual number of atoms in each molecule, is C2H2. Compare that to benzene. Benzene is C6H6, okay? So benzene has basically 3 times the number of carbons and hydrogens than acetylene does, okay? So basically, all you need to know from here, oh my goodness, look at my writing. That looks terrible. I'm just going to erase that. Hopefully you guys have it written down. Basically, your empirical formula is your molecular formula reduced, okay? Or your empirical formula is also what we use in ionic compounds. So remember, when we name ionic compounds, if we're doing our crisscrossing, we also have to remember to reduce, okay? So if we reduce, it's an empirical formula. If we don't reduce, it's a molecular formula. So have a look at these. Can you classify the following formulas as molecular or empirical? So in your notes, underneath or beside each one, put an E for empirical, reduced, or an M for molecular, not reduced, okay? So pause the video and then I'm going to take up the answers. All right, so answers BH3, I cannot reduce that anymore, so that is an empirical formula. B4H10, I could reduce this down. I could divide both by 2 and reduce it to B2H5, so therefore this one is a molecular formula. B5H7, I cannot reduce, it's empirical. B5H11, I cannot reduce, it's empirical. And B6H12, I can reduce down to BH2 if I divide both of those numbers by 6. So this is also a molecular formula. Okay, what I want you guys to understand is the difference between the two, but do not, if it's a molecular compound, do not reduce. You're not supposed to reduce unless you need or you are asked to find the empirical formula. So when you're doing your street naming, the only time you can reduce is for an ionic compound. So hopefully that's clear for you. All right, now how do we calculate these empirical formulas? So basically what we're doing right now is the reverse of what is in the last video on percent composition. So the empirical formula of a compound can be found from the percentage composition of the elements in the compound. And the following rhyme is what I use to help you guys remember the steps. So step 1 is percent to mass, step 2 mass to mole, divide by small, then multiply to a whole. Percent to mass, mass to mole, divide by small, multiply to a whole. Okay, and these are basically the steps sort of written out, okay? So the first thing we're going to do is assume that we've got a 100-gram sample of whatever we're talking about, and we're going to change whatever percentage it is to mass, and that's how we calculate the grams. Then we're going to take that mass, use our atomic weights to calculate the moles, and then we're going to calculate the molar ratio for each element by dividing by small and multiplying to a whole, and then assign the empirical formula. So I know this is a whole lot of words and you guys might not fully understand what it all means. So I think the best way to explain it to you is going through an example with you. So here is example number 1. I'm going to move my little arrows over here. So a compound consists of 72.2% magnesium and 27.8% nitrogen by mass. What is its empirical formula? So notice in the last video I gave you a formula and I asked you to find the percent compositions. In this video I'm giving you the percent compositions and I'm asking you to find the formula. So you're sort of doing the reverse. So I give you this chart here to kind of talk you through the little riddle. Percent to mass, mass to mole, divide by small, multiply to whole. So I'm going to talk you through that right now. So your first step is to find the mass of each element. So all we're going to do is assume that we have 100 grams. And we're going to take these numbers and fill them in. So I've got 72.2% magnesium. I'm going to call that 72.2 grams of magnesium. And then I've got 27.8% nitrogen, so I'm going to call that 28.8 grams of nitrogen. So now I have to change that into moles. So how do I do that? So to find the number of moles of magnesium, remember what I'm going to do. I'm going to take the mass, so in this case 72.2 grams, and I'm going to multiply by the conversion factor, which basically means that I'm going to divide by the molar mass of magnesium. So this is what we've been working on in class. So if I do that, then I'm going to get 2.96 moles of magnesium. So that's what I'm going to write in my box up here. Okay, then I can do the exact same thing for nitrogen. Find the number of moles of nitrogen. If I have 28.8 grams, again, I'm going to end up dividing by the molar mass of nitrogen, which is 14.01 grams per mole. So when I do that, I get 1.98 moles of nitrogen. So I'm going to put that number in here. Now I'm showing you all the steps in this one. I'm not going to always do that because I'm going to start to assume that you guys know how to change between grams and moles really, really easily. Okay. So I did percent to mass, check, mass to mole. Now the third step in the riddle is divide by small. This is easy. You're actually going to take both numbers and divide them by the smallest of the two numbers. So if I look here, the smallest number is 1.98. So I'm going to divide this by 1.98 and divide this by 1.98. So I'm going to divide them both by the smallest number. What that does is it gives me 1, and if I do this, it's 1.5. So that's divide by small. Now I have to multiply till whole, which means that if I have a decimal place in my ratio of moles column, right here, if I have a decimal place here, I've got to multiply this out to make a whole number ratio. So in this case, I'm going to multiply everything by 2. So I get a 3 to 2 whole number ratio. And this is what's going to be my formula. So I'm just going to bring this down here. And what this tells me is I've got 3 magnesiums, so Mg3, and I've got 2 nitrogens, N2. So fancy dancy little riddle basically takes the percent composition and turns it into an empirical formula for you. Okay, let's do one more. I'm going to not talk you through as many steps in this one, but that's how you do it. So, sorry, before we do that, the empirical formula and the molecular mass of the compound are required if you want to calculate the molecular formula. So what I just did on the last slide here, that's the empirical formula. It's the reduced formula. So if I need to find the molecular or the unreduced formula, I have to take into account a little ratio. So for example, I found the empirical formula of a compound, and it was found to be C1H1, or just CH. Okay, there. Then it says its molar mass was also found by experiment to be 78 grams per mole. What is the molecular formula of the compound? So this is actually really easy as long as you know what the formula is. So the formula that I use is the molecular mass, or the molar mass, sorry, of the molecular formula divided by the molar mass of the empirical formula gives you some sort of a ratio. Okay, so if we do that right now, I'll do that in blue. I've got the molar mass of the molecular formula. That's my 78 grams per mole. It's always the bigger number. And if I divide that by the molar mass of the empirical formula, which is 1 carbon and 1 hydrogen, that's 13.01 grams per mole. If I do that, my whole number ratio, or my ratio in this case, is 6. So what that means is you're going to take your empirical formula, which in this case is CH, and you're going to times everything in there by 6. So it ends up giving you C6H6. That's your final answer for the molecular formula of a compound. All right, so let's do one of those right from the start, right from using percent composition. A reactive compound contains 13.2% boron and 86.8% chlorine by weight. If the molar mass of the compound is known from a separate experiment to be 163 grams per mole, what is the molecular formula? So again, percent to mass, mass to mole, divide by small, multiply to whole. That gives us the empirical formula. So let's put in our elements. Here I've got boron and chlorine. My first step, percent to mass, is just literally recopying it into grams. 86.8. So I take my percents and I recopy it into grams. Then I'm going to divide by the molar mass to convert it to moles. So I did percent to mass, now I'm doing mass to moles. So in this case, if I do that, I'm going to do 1.22 moles here and 2.45 moles for chlorine. Next step in the riddle is to divide by small. So in this case, I'm going to divide them both by the smallest number, which is 1.22. And that gives me a whole number ratio, or a ratio of 1 to 2. Then multiply to a whole, I don't have to do because I already have a whole number ratio. So I already have a 1 to 2 ratio. So in this case, the empirical formula of my compound is BCl2. I've got 1 boron and 2 chlorines. All right. But that doesn't answer the whole question, okay? The final question is asking me to find the molecular formula, so the unreduced formula. So remember, to do that, I need to find that ratio. So the molar mass of the molecular formula divided by the molar mass of the empirical formula will tell me what number I have to multiply it by. So in this case, my molar mass of the molecular formula is always given to you in the question. Always, always, always. And it's always going to be the bigger number. So in this case, it's 163 grams per mole. The molar mass of my empirical formula, I use this BCl2. So 1 boron plus 2 chlorines gives me 81.71 grams per mole. And when I do that, it gives me a ratio of 2. So that means I take my empirical formula, BCl2, and I'm going to multiply everything in there by my ratio from here. So if I do that, my final molecular formula will be B2Cl4. And that's pretty much as tough as it's going to get. The last example I want to go through with you is hydrates. And for some reason, again, people find hydrates really, really complicated, but they're really not. So I want to talk you through a quick example of that, and then we're done. Oops. There we go. So look at this hydrate example. Consider the following. If I have a gram of magnesium sulfate heptahydrate or a gram of just straight up magnesium sulfate, which one do you think has more magnesium atoms? So if you think about it, here a lot of the mass goes into the water, whereas here I have no water to take up any of my mass. So that means I'm actually going to have a lot more magnesium atoms in my anhydrous or not hydrated compound. So let's look at an example using percentage composition, or in this case masses, to find the formula of a hydrate. This is actually going to be one of your labs, so you might want to pay close attention to this. So 50-gram sample of a barium hydroxide hydrate contains 27.2 grams of barium hydroxide. calculate the percent by mass of water, and find the value of X. Here's my hint to you whenever you're doing hydrate problems. Treat the barium hydroxide and the water as two elements. So that's what I'm going to do in my chart here. So I'm going to put barium hydroxide as one element and water as another element. And then I'm going to follow my riddle. So in this case, I didn't give you any percentages. I gave you the masses straight up in the question. So I know I have 27.2 grams of barium hydroxide, and the rest of my 50-gram sample is going to be water. So in this case, it's 22.8 grams. That's water. Now what I have to do is I have to divide by the molar mass to get to the number of moles, okay? So in this case, I have to divide by the molar mass of my entire barium hydroxide. So when I do that, hopefully that's easy for you. You should get 0.158. If you're not getting that, come and see me in class. And then if I, again, take 22.8 divided by the molar mass for water, I get 1.27. Third step in this process is divide by small. So I'm going to divide them both by the smallest number, which is my 0.158. Make sure you're always dividing by the same number here. And when I do that, I get a ratio of 1 to 8. So my whole number ratio, I don't have to worry about any decimals in my ratio, so I just leave it alone, and I use 1 to 8. So that means that for every 1 barium hydroxide, it's hydrated with 8 H2O molecules. So therefore the formula is BaOH2 dot 8 H2O. So the name for this would be barium hydroxide octahydrate. All right, that's the end for calculating empirical and molecular formulas. If you have questions or if you're not getting one of these steps, please come and see me right away in class.